Welcome back to Applied Algebra and Trigonometry. Let's look at some more trigonometric equations. Now, there is one important point about solving these equations that I did not cover yet because I wanted to show it to you in the context of the next example after I do a little discussion here, because then it will make more sense. But basically, take a look at sine x equals 1/2. It's positive. Our answer is going to be in quadrant 1 or quadrant 2. So our reference triangle, our reference angle, would be 30 degrees. Let's do this in degrees since that's most familiar to all of us. So that would be 30 degrees in our reference triangle, 30 degrees in this reference triangle, 30 degrees in that reference triangle. Remember, the answer can only be in quadrant 1 or quadrant 2, but we can think about this as swinging that side with length 2 around to either position. But what if we continue swinging it? We'll hit this one again, we'll hit this one again, we'll hit this one again. This can go on infinitely unless we restrict it. All of the examples we have done so far are restricted such that 0 degrees is less than x, which is less than 360 degrees. And if we express that in radians, 0 less than or equal to x, which is less than 2 pi. We don't let it equal 2 pi or 360 degrees because we don't want to count the initial angle twice. We're going to keep that restriction in place. X will always be between or equal to those values. However, the last set of formulas we worked with were double angle formulas. We were playing around with 2 times x. Let's keep those two concepts in mind and apply them to an example. Here is the equation to solve, and there's a reminder of the restrictions on x. So the first thing to do is analyze what we have here. We have 2x and we have 4x. It appears that we have two different angles. However, 4x is equal to 2 times 2x. What if 2x is our alpha? And we think about this as the sine of 2 times 2x minus the sine of 2x, or the sine of, doing our substitution, 2 alpha minus the sine of alpha. We know from the double angle formula for sine that the sine of 2 alpha equals 2 times the sine of alpha and times the cosine of alpha. And all I've done is replace sine of 2 alpha. I still have to subtract the minus sine of alpha, and it still equals 0. All right, let's go back to our original angles now. Everywhere I see an alpha, I'm going to substitute a 2x. So 2 sine of 2x cosine of 2x minus sine of 2x equals 0. It looks more complicated so far. I have two terms. I have lots of stuff multiplied on the left, or in the left term, and then I have a sine of 2x. But wait a minute, that sine of 2x is found in both terms. I can factor that out as a common factor. So removing the sine of 2x, I'm left with 2 times the cosine of 2x minus 1 equals 0. There are different ways we could go from this point. We do have a double angle. We could split that up. We do have a double angle in here. We could expand that. But I would argue there are better ways to deal with this. I have two factors. There's one, there's another. If either of those factors is equal to 0, when you multiply them, the answer will be 0. So we can set each of them equal to 0 and solve. So 2 cosine x minus 1 equals 0. Okay, I'm going to double check, make sure I am back to my original variable. Yes, I am. It was x. Okay, but now I got to start thinking about that double angle. I just said I didn't want to expand it, so what else could I do? I'm going to leave the second factor alone for a while and explore all the possible answers to the sine of 2x equals 0. Now, the interesting thing is that we have constraints upon x that I listed up there, okay, at the top. However, those aren't restraints on 2x. If those are the restrictions on x, the boundaries of x, what would the boundaries of 2x be? Well, 2x is 2 times x. So 2 times 0 is 0, and 2 times 2 pi is 4 pi. So 2x is restricted to 2 rotations around the origin. So let's go ahead and graph that now. Where is the sine of 2x equal to 0? Here, where 2x equals 0, or if we swing it around, 2x would equal pi, and if we swing it around, 2 pi, we swing it around again, 3 pi, keep swinging it around to 4 pi. Except we can't go all the way to 4 pi. We're restricting that. We already counted that as 0. We counted it as 2 pi. We don't want to recount again. We just want 2 complete revolutions around the origin there. So let's move this out of the way just a little bit. Oops. All right, and now we can turn our attention to the other factor. 2 times the cosine of 2x minus 1 equals 0. We will now go through a series of algebraic steps. I'm going to add 1 to both sides. And divide both sides by 2. So we have the cosine of 2x equals 1/2. Where is that true? That is true in the first quadrant and in the fourth quadrant. Now, what will that look like, though? The cosine of 2x, we need an angle, equals the adjacent over the hypotenuse. And if we draw the reference triangle, look at that. It's a 30, 60, 90 triangle. So 2x is found in this first quadrant. I'll go ahead and do it in white. And in the fourth quadrant, that is where you can get a positive cosine value. The angle that we're interested in our reference triangle is pi over 3. So this first angle would be pi over 3. So we also have the answers writing down here at the left. Pi over 3. And continuing around, we reach 5 pi over 3. Going further, we reach 7 pi over 3. And finally, the last angle that we reach before we get to 4 pi is 11 pi over 3. But those are not our final answers, because that's what 2x is equal to. We need to break those apart a little bit. First, let's put them in order from smallest to largest. I think that might help seeing the whole thing a little bit better. 2x equals 0, pi over 3, pi, 5 pi over 3, 2 pi, 2 pi, 7 pi over 3, 3 pi, and 11 pi over 3. That's what 2x is equal to, each individual one of them. So if we divide everything by 2, we get x equals 0, pi over 6, pi over 2, 5 pi over 6, pi, 7 pi over 6, 3 pi over 2, and 11 pi over 6. And remembering, okay, there's my little memory bubble. We have our angle greater than or equal to 0 and less than or equal to 2 pi. Is that true for all of those values? Yes. You may check each of these final values in your calculator to see if when you put it into our original equation, which we see there, it will equal 0. Some equations have a multitude of solutions. Rewatch this example if you need to. We will talk about this process during our Collaborate session. Talk to you then.